Hello, everyone. My name is David Babb. I'm here on behalf of the IGS, the group that coordinates the IGS Global Seminar Series. This week, we are thrilled to have Heine Prinz. Sorry, misread your name. Heine Prinz from the University of Innsbruck, who's going to be outlining three Hintereisferner experiments and their boundary layer studies on an Alpine glacier. So, as per usual, the seminar is being recorded and will be uploaded to the IGS YouTube page. We only have one presenter this week, so he has the entire time. I ask that you save your questions until the very end, when you can either raise your hand or drop them into the chat, and we'll go from there. So without further ado, I'll pass it over to Heine.
Thank you, Dave, for the introduction. So, hello to the audience. Good evening from my side. It's evening on my part of the globe currently. My name is Rainer Prinz from the University of Innsbruck in Austria. I'm working at the Department of Atmospheric and Cryospheric Sciences, and I'm introducing the Three Hintereisferner experiments, the boundary layer studies on an Alpine valley glacier. And well, I have to say, was more into logistics of the experiments, and also, of course, a little bit contributing with my scientific and local expertise to that. But actually, the engines and brains in the experiments were Lindsay Nicholson and Ivana Stybalski, also from Department of Atmospheric and Cryospheric Sciences here in Innsbruck. And there was a contribution from Rebecca Mott from the SLF in Davos in Switzerland, and Tobias Sauter from the University of Berlin. And I very much want to advertise those two guys here, Alexander Georgi and Leo Schlagbauer, who are currently PhD students at our department working with data from the third Hintereisferner experiment, and there's hopefully more to come from them. And of course, there were many, many more people involved in these experiments, and I don't have a list of name here, but I have a list of all the institutions. I hope did not forget anyone, but it's a list of all the institutions that somehow contributed to those experiments. It's from Innsbruck and Berlin, of course, but also University of Erlangen-Nuremberg, University in Augsburg in Germany. We had the Swiss contributions from the SLF, the ETH, and University of Bern. We had University of Graz in Austria, of course, University of Grenoble, Western Norway, Northumbria and Leeds, and so on. And in the bottom line, you see the most important funding agencies, especially the second Hintereisferner experiment was supported by the ERC from Ivana Stybalski, the first and second experiment by Interact, which is a European Horizon 2020 project, and especially the last experiment by the German and Austrian science foundations. Okay, before I go into the experiments, I show you a little bit background and context of Hintereisferner. And so the location of Hintereisferner, it's the blue one, the dark blue one here on this map. And the location is in Western Austria, right at the border to Italy. And Hintereisferner is embedded in this research catchment that we call Rofental. And this research catchment is depicted by this red line here. It's about 100 square kilometers wide, and it hosts these three glaciers, which are called reference glaciers in the World Glacier Monitoring Service. A reference glacier is a glacier which has more than 30 years of continuous mass balance observations. And Vernachtferner is monitored by the colleagues of the Bavarian Academy of Sciences in Munich. Kesselwand and Hintereisferner are basically monitored by us here in Innsbruck. And you see a lot of colorful dots here. It's all weather stations with different sensors, weather stations for different purposes, weather stations from different organizations. This is kind of how it grew historically in this catchment. And it's a very, very good collaboration with all those institutions, providing data, working together, and having quite nice cooperations. Now, on Hintereisferner, everything started a little bit with this image here, and it's supposed to be the oldest image of a glacier from mankind, drawn in 1608 by Abraham Jäger, and it shows Vernachtferner, so this guy here. And in the Little Ice Age, it advanced down valley into the main valley here and blocking the runoff of those glaciers here in the back, forming an ice-dammed lake in about this area here. And you can see this ice-dammed lake, and this ice dam collapsed in 1600, caused some devastations in the valleys or down valley, and actually also in Innsbruck. That's why the emperor sent a commission up to in the mountains to look what's going on here. And this is basically the start of the kind of glaciological research in the area. So more formalized, then it got a little bit late in the mid of the 19th century, that we can call Hintereisferner as a kind of open air laboratory. And we have glacier length changes since observations of glacier length changes since 1847. And what's written here in bold are observations or programs that are still ongoing. We had a borehole drilled through the glacier down to the bedrock already in 1894, because the people wanted to know how thick the glacier is. We have measurements of surface velocity since 1894. We had early theories on ice dynamics in 1907 until the 1920s. We had seismic ice thickness measurements in 1927, and this was actually a test of the seismic method to measure ice thickness, which then Alfred Wegener brought to Greenland in 1930 or 1929 to measure the ice thickness of Greenland as a first person. We have programs and measurements of the micrometeorology of glacier wind already in the 1930s, energy balance 1952, and radiation in 1955. We have a mass balance program since 1952. We have a hydrometeorological program since 1966, and also some exotic things like investigations of the nuclear physics of glacier ice in 1970. So this is just to show you that Hintereisferner is really one of the maybe best examples to do also observations on boundary layer above the glacier. And additionally to that, we have the TEAM-X program, and TEAM-X is an acronym that stands for Multi-Scale Transport and Exchange Processes in the Atmosphere over Mountains. And it's a community program that is led by the University of Innsbruck and focuses on exchange processes between the land surface and the atmosphere, and especially in mountainous and complex terrain. And in this complex terrain, we also find glaciers, and that's why we have a sub-working group of glaciers led by Lindsay Nicholson here in Innsbruck, Toby Sauter from Berlin, and also from Jean-Emmanuel Sicard from the University of Grenoble. So that's basically kind of setting the scene where the Hintereisferner experiments are somehow embedded, and what our basic framework and is where we also develop our concepts. So let me come to the Hintereisferner experiments. We had 3 of them in 2018, 2023, and 2025. And the basic concept is shown here in this schematic of the glacier wind system, which we actually want to measure or characterize. So when I speak of the glacier boundary layer, I mean this thin air layer above the glacier surface, and this glacier, or this thin air layer, gets constantly cooled, because in summer the glacier ice is usually colder than the air above, and so how we have this constant exchange of energy and cooling of this air layer, forming a katabatic wind system with a low-level jet. And this katabatic layer is actually damping low-frequency perturbations that are brought from outside of the system, either by the up-valley wind or by lateral attraction. And the idea of this Hintereisferner experiments were actually to better characterize the different or specific settings of the glacier boundary layer, especially towards advection and up-valley wind, and to also investigate how strong this dampening function or dampening process is. Now, the first experiment was carried out in August 2018, and if I want to characterize the 3 experiments, we can say that the first experiment was more or less the specific case, and where we wanted to investigate the structure and the katabatic layer along the glacier and also on a half cross section on the glacier. So interesting questions were what is the role of the horizontal heat exchange by advection and also the influence of potential atmospheric gravity waves on the katabatic layer down here in the glacier down. There was also a side project on aerodynamic roughness lengths of glacier ice, which is nicely described in these two publications here. But for the interest of time, I'm not going to talk about this. If you want to characterize or well, show how this boundary layer could look like, we could look at this image here, and it would be actually a movie, but I thought I don't show the movie because on this Zoom sessions very often we have a time lag in these movies, and that's why I thought it's better to just show screenshots. But you see a thermal camera image. So the blue is the black glacier surface. The red thing in the background is basically rock surfaces that get heated up by solar radiation. You also see the cold meltwater streams coming down here. And you see these screens on the glacier surface, 2 meters tall and about 5 meters or 6 meters long. And you see in the movie, we would actually see the cold air traveling down glacier, but you see that this air is stably stratified so that you have the cold air down to the glacier surface and the warmer air aloft. And you see actually already here that there's a kind of a warm air blob. And in the next image, you see how this blob will propagate. And you see here at the time indicated here, it's 5 seconds and almost 17 seconds. So in this little bit more than 11 seconds, you see that this warm air has traveled down here into the boundary layer, causing some intermittency and some also maybe some erosion of this boundary layer. And this would just see here in the schematic that we have this katabatic layer, and the jet maximum is just very close to the surface, but the jet maximum causes some shearing, and this shear introduces the intermittent bursts that then travel down to the glacier and just bring some more exchange of energy with them. So if you want to characterize or just say something about the observations of the boundary layer processes in the first HAFEX campaign, where we actually were interested in what is the role of the different direction of the synaptic flow on the glacier boundary layer. We saw especially that westerly synaptic flows disturb the prevailing boundary layer and form a cross glacier flows and facilitating warm advection from the surrounding ice-free areas. So that we had an advection from the warm ice-free areas. And I'm sorry, that's a slope map here. So that's not temperature, that's a slope map. But you can just imagine that from the warm slopes, we get advected, warm air advected towards the glacier. And interestingly, this effect is strongest on the center line, and the peripheral zones, they seem a little bit sheltered to these processes. But so these were the observations, but we also were able to put this into a model, and this was a nice work by Brigitta Goga. And what we see here are cross sections across the glacier, actually at this cross section here, and we see 2 glacier surfaces. Then in this cross section, we see the glacier down valley and also this glacier surface a little bit higher up. So this is indicated by these white lines here. So we see the glacier higher up and also the glacier down in the valley here. In the colors, we see the turbulent kinetic energy as a kind of a measure for the turbulent heat exchange. And in the contours, we see the potential temperature. And in the top row, this is the rows are 2 different days, and the columns is just time from 6 to 12 UTC. And the top row would be just a day with a classic evolution of a katabatic boundary layer with a very stable stratification above the glacier. And in the bottom row, we see that in this case, with a northwesterly synoptic flow, we induce a gravity wave on the crest to the north, which would be the right side here. And this gravity wave is traveling down valley and then completely eroding the glacier boundary layer causing a lot of turbulence, kinetic energy, and more heat transport towards the glacier. And we can say that the synoptic wind direction has a strong impact on whether a glacier boundary layer can form or not, and this influences whether a glacier is stable, a glacier is able to maintain its own microclimate. And in a later modeling study from Brigitte Goga, she's also showing the influence of the glaciers upstream when we just put them out of the model, that there's even more turbulence kinetic energy introduced and even more warm air advected to the glacier then. So coming to the second Hintereisferner experiment in August 2023, and this is more or less an extension of the first experiment, where we just go from the specific more to the general case. The questions somehow stay the same. So we just ask what's the glacier boundary layer properties, especially persistence and controls on katabatic winds, and the spatiotemporal variability of the micromorphological conditions on the glacier with respect to the surface energy balance. But not only on a small part of the glacier tongue, we really had a distributed view over almost the whole glacier surface. The last question, the upscaling from the station observations to the valley scale atmosphere, we actually postponed a little bit to the third experiment, which I show you later. So this is a map of the weather stations we installed on the glacier, and this was really a very intensive campaign because we had 10 multi-level eddy covariance stations, so that's all the red dots here, and 2 of the 10 multi-levels were even 5-meter tall towers. I'll show you a picture later. We had 9 auxiliary weather stations working on low frequency. Low frequency here means recording at 10 minutes. The eddy covariance station were recording at 20 hertz. We had over a few days short path ultrasonic anemometers very close to the glacier surface, providing for the towers a 4th level of observations. We had again high-speed thermal camera imaging. We had meteorological UV soundings, and we had off glacier at our research hut. We had a streamlined Doppler lidar for wind profiling of the atmosphere. So this is an image of the weather stations we employed. To the left, it's a 5-meter tall tower where we had 2 of them with permanently 3 levels of turbulence measurements. We had 8 of these stations in the center where we had 2 levels of 3D sonic anemometers, and the auxiliary weather stations looked somehow like this. On all the weather stations at the 1-meter level, we had an Irrgasson, so also measuring water vapor and CO2 fluxes, and at the 2-meter level and 4-meter level, we had standard CSATs. This is just an image on the observations on one of the towers, where we see in 10 minutes aggregated the vertical profiles of wind speed on the top row and temperature in the bottom row, and clustered into 3 clusters. We had 2 katabatic clusters, the first one and the second one. And in this right image, we see the diurnal frequency of those clusters. So the red one would be a daytime cluster because it occurs mostly during the daytime hours. The yellow one, a nighttime cluster, and the green one is a kind of a disturbed cluster. And we see in the katabatic clusters that we have a wind speed maximum on about 1.5 or 2 meters above the surface. So these katabatic jets are very shallow. And then we have a decreasing of the wind speed. And in the disturbed cluster, we don't see any wind speed maximum. And it's actually not a katabatic cluster because it's purely driven by the synoptic flow. We can also have a look at the flux distribution of the turbulent fluxes, of the sensible heat flux to the left and the latent heat flux to the right. There's nothing really surprising in here. So we see that we have a constant supply of energy to the glacier surface, of course, a little bit less higher up the glacier, and a higher sensible heat flux further down the glacier. For the latent heat flux, it's also not very surprising in summer that we have more or less constant condensation of water vapor on the glacier surface. A little bit interesting is this lowest station here, which was actually built on a debris cone. So we have a few centimeter thick debris layer on the glacier, but we have not final analyzed the data. So, but it might be just interesting what it shows you. Coming to the third Hintereisferner experiment last year in August 25, which we also call the glacier space experiment. And this is where we try to link the glacier boundary layer to the valley atmosphere aloft. And we have seen this image before. And what the basic idea of this glacier space project is that glacier somehow self-generate a glacier microclimate that creates as a safe space more amenable for glacier survival than the ambient environment. And this is basically reflecting on this dampening effect of low frequency perturbation. And we think that as the glaciers retreat, this glacier boundary layer might get weaker and easier to erode by lateral advection or also by processes induced by upvalley winds, and that turbulent motion transport more heat towards the glacier surface as glaciers become smaller and steeper, and that we might see a rapid glacier retreat that leads to a loss of the microclimatic shelter of this safe space, and to finally positive feedbacks and increases in glacier vulnerability to ongoing climate change. And this is basically what we wanted to observe here. And as this project is quite young, I can only show you some observations and some measurement concept. So the basic point here is a almost 10-meter tall tower with, again, turbulence measurements. And we just link the scales by having also two wind lidars operating on the glacier with a wind range up to 200 meters above the surface, and another lidar with a streamline lidar range reaching up to 1,500 meters above the glacier surface. And we try to extend this information or these measurements across the glacier using UAVs with meteorological sensors. So in a way that we have high quality observations serving then later for coupled glacier atmosphere modeling that in the end then should provide the sensitivities of these feedbacks that we think then kick in as the glaciers get smaller and the boundary layer might get easier to erode. Now showing you some pictures how this looks like. So we had for a month we had two wind lidars operating on the glacier surface, which maybe we were the only one doing this. It was not easy because those instruments need a lot of power. We also had almost 10-meter tall tower installed on the glacier with 5 levels of 3D sonic anemometers and a lot of auxiliary meteorological instrumentation. And then we had also a couple of UAVs flying regularly or profiling regularly the glacier atmosphere with these meteorological sensors measuring temperature and humidity. And we also had these self-built radiation shields around the sensor to minimize the effect of solar radiation or solar heating of the sensor. As a kind of, another experiment, what we did is that we employed a terrestrial radar interferometry above the glacier. And the idea is that by analyzing the propagation delay of the emitted signal of the radar interferometry, we aim to directly measure the atmospheric moisture field above the glacier. Because moisture in the line of sight of the radar interferometry would delay the radar signal, and in a way that it would look like that the glacier is flowing uphill, but we know that the glaciers are not flowing uphill, so there must be something else that the signal is distorting, and the only way this can be is actually atmospheric moisture in the line of sight. And this is a kind of an experimental setup where we try to investigate that. Um, as the project is quite young, I can't show you much more analysis out of it, but I also want to come a little bit into logistics of that because it's not easy to do that on a glacier. But Hintereisferner is large enough to be considered as a kind of a glacier, so it's about 5 kilometers in length and well, a couple of 100 meters wide. So in total, it's almost 6 square kilometers, and it's large enough to be a glacier, small enough that most of the stuff can be done by foot and by walking. And luckily, we have also this research hut, which is also kind of a safe space for our fieldwork crew. But as we know that weather conditions are not always nice and sunny, they can also be some kind of miserable. And then it's nice when you have a shelter and a cozy bed and a warm soup. Many thanks also to the crew who operated the UAVs because they basically lived on the glacier as they had to do their UAV flights every 3 hours, also in the night, and they were provided with food and with some support. But once a day they walked up also here to our hut to get some warm food and some company and some social exchange. Of course, before you install a lot of sensors on the glacier, you have to do some comparison measurements and also to do some setups and sensor testing, and so to be sure that when you install them in the field, that everything works nice and sweet. And you see here Ivana Stibelski sitting on the roof of our department, just testing all the 3D anemometers mounted on this mast here. Just a word on a special situation. During the second Hintereisferner campaign, we had kind of a severe weather system moving in. So you see this low pressure system over the Gulf of Genoa, providing with a lot of moisture from the Mediterranean Sea, and you see that temperatures were really dropping below zero here end of August. But the main problem was the precipitation we received here, and there were numerous stations across Western Austria that recorded more than 150 millimeters of precipitation, more than 72 hours. And this in the end resulted in peak flows with a return period of above 100 years, and we had some floodings in the area, which did not affect the people on the hut, but it affected the main access road to the research catchment. And we had we could not stay with the schedule exchanging the personnel on the hut, but luckily we were all flexible enough to compensate these unforeseen issues. So coming to an end here, and to conclude, so we had more than 400 person nights in the field with all the 3 experiments together, more than 800 helicopter minutes, and we are still sitting on terabytes of data where numerous students, master students, PhD students, and also researchers are analyzing, and we have a couple of papers in the pipeline that should be submitted in the next couple of months and hopefully also in the next couple of years. And the Hintereisferner experiments were probably the most comprehensive glacier meteorological campaigns ever conducted on mountain glaciers, and also can be seen as a further and a logical development of previous campaigns, as we had, for example, the Bastex campaigns in the mid-1990s. And we tried to bridge the scales from kind of local to glacier-wide boundary layer observations, and also extending the observations vertically out of the glacier boundary layer, connecting to the valley atmosphere, with the final goal that we have an assessment of the resilience and vulnerability of mountain ice to these potential feedbacks that I introduced to you, that as the glaciers get smaller, the boundary layer might get more vulnerable to be eroded by processes happening outside the glacier. And yeah, with that, thank you for listening, and open to questions.
Great. Thank you very much. That was an impressive amount of work done in that project. I'll open it up for questions here. If anyone would like to raise their hand or drop it in the chat. Oh,
I'll go
yeah.
ahead since I don't see
Yeah.
anyone else's hands raised. Thanks for that great talk, Heine. I'm curious about a bunch of things, but in one of the earlier sections, I think you said it was the result of experiment one or two. Um, it looked like the depth or even the setting up of this like boundary layer depended also upon what the synoptic airflow was doing. And I'm curious how much of that was specific to Hintereisferner and how much that would be, yeah, how does that impact how transferable the results are from like this glacier to understanding that process on other glaciers as well?
That's a very good question because it somehow deeply affects what we are working in on our department. That what are really the exchange processes in complex terrain, and are we able to somehow transfer it by maybe parametrizations we find. But so far, I would say that this is very specific to the topography of Hintereisferner, having this kind of long glacier tongue, kind of deeply incised into this valley. Um, I could very well imagine that is similar to other classical valley glaciers. Uh, but then, of course, it depends on their orientation, and it depends also how their katabatic system would evolve um, com in consideration with the general synoptic flow. So, as a specific case, I would say. Yeah.
Thanks.
Others, any questions?
I have another question, but I don't want to interrupt other people if they're going for it. Um, I'm curious about the breadth of instrumentation that you used. And one, if you could talk, I had never seen a TRI used to look at atmospheric moisture before. Are there other places where you know that that's been done, to maybe do a little bit more reading? And two, yeah, there was a lot of instrumentation. It were I'm trying to think of the right way to say this, but like, was it all worth it? Do you think it's all going to be helpful and important, or were there, in retrospect, some things where like, this was the most important stuff. This is really what helped us understand these systems. And you know what? We actually didn't need this other this other sensor, or we didn't need it at this resolution. If people are thinking about their own monitoring systems or experimental systems.
I would say we are maybe not that far to answer that. Um, the disadvantage of the second Hintereisferner campaign, when I want to say it like that, is that it was not a campaign where we had a project standing behind it. It was just a community effort where we just said, "Hey, let's do cool stuff on a glacier. Come to Hintereisferner. We provide you with food. You bring your instruments, and then we do a cool measurement experiment." It worked out very nicely, but the disadvantage is that if when there's no project framing it, then people don't take time to analyze the data, and it's basically a little bit on the well on the individuals if they raise money or if they find students working on it. Um, yeah, I would say it like that. But we are slowly progressing. We're sitting on a bunch of data, and as our emeritus professor said, well, there will be generations of PhD students analyzing this bunch of data. I hope it's not generations, but at least there will be a few of them. For the questions with the TRI, this is actually very, very new, and it's an alumni of our department who just came back as a scientist now to Innsbruck, and he developed this method during his PhD, and then later as when he did a postdoc in Oregon. And there was a preliminary campaign in Switzerland, and this will be published soon, I think. And so the follow-up campaign was then Hintereisferner. And it looks very, very promising that you really see moisture fields traveling along glacier because well, it's just a residual what you see in the signal.
Cool. Thanks. Yeah, I'm getting some information in the chat about it too.
Anyone else? I wanted to ask quickly just about the three clusters of sort of wind conditions that you guys observed. So you observed the nighttime kind of typical conditions and the daytime conditions, but the third, was that related to just storms passing through the area, or was there a specific forcing related to that?
Yes, and this was a storm passing through, and this is also then the same signal as I showed you in this model experiment that we just had synoptic flow from a completely different direction and inducing then basically up valley winds, well, all the time as long as the storm passed through. So there was no katabatic system evolving during that time, and
Okay.
it was just a completely disturbed setup there.
Okay. Interesting. Well, if there is no other questions from the chat, I think we will call it there. Oh, here we go. Last one from Ian. Did you collect any information on seasonal variation in the GLGI wind?
What's a GLGI wind?
I'm assuming that means glacier
GL
wind.
Okay.
Okay. Um, no, sorry, no really seasonal information because the experiment only lasted for a month each in the core summer season, and I mean we have a weather station operating throughout the year. The problem is that in winter it's 4 to 5 meters of snow, and eventually even the anemometer is buried, and during the summer maybe it's broken after this much of snow. So it's all the problems with doing measurements continuously on a glacier surface, but definitely no three-dimensional wind measurements over the year. So no seasonal information. Sorry.
Okay, perfect. Thanks. Okay, I think we'll wrap it up there. Thank you very much for your presentation. Thank you for staying up late this evening to do this. We really, really appreciate it. It was a really great presentation and seems like an awesome project, very collective and lots of teamwork taking place in it. I really, really enjoyed it.